In this video, I am building an extremely high-resolution portable medium format camera using a linear scanner sensor by reverse engineering the sensor, developing a user interface, and integrating it into a completely new camera without reusing any of the other original scanner parts. Large sensor sizes have some benefits regarding resolution, depth effects, and sensitivity. Think of how the image of a good full-frame camera can look compared to a phone. For example, this video is shot on an A6400 with an APS-C sensor. While full-frame cameras aren't cheap either, medium format sensors are a whole different story and quite rare as well. In the end, this scanner camera will exceed all commercially available cameras in terms of resolution for a fraction of the cost, while being capable of taking images in resolutions of over 3 gigapixels in 80,000 by 40,000 with 16-bit color depth per sample in true color without even using a Bayer filter, with the major restriction of only being able to capture static and well-lit objects. For this project I bought two scanners, an Epson V300 and V370. They were both part of the same offer on eBay and they were sold as defective. The V370 advertises a slightly higher resolution than the V300, but I found a service manual of the 300 and did list the same resolution of the sensor. They might possibly even share the same CCD sensor and probably most of the processing components. So this is how it looks like with the lid removed. We can see the sensor assembly with the optics. The CCD is on this board, on this carrier. Then there seems to be a lens and mirror assembly which projects the document onto the actual image sensor. I had tried to compare this board with a schematic I found for the V200 scanner. It did look very similar in terms of components, but it is not completely identical. So the Epson branded parts, which is this chip next to the USB port, and on the bottom we have this also Epson branded BGA part, which seems to be connected to DRAM chip. This is also not identical, but on the V200 it looked like a digitally controlled motor driver. One difficulty which I have seen in similar projects is that these scanners must see a white calibration reflection strip which is under the glass on startup. Otherwise there will be an error, as we can see now. Now it is not seeing the reflection and it's not going away, and it will blink orange. So while disassembling the optical unit, I wanted to take some macro shots. When we take out the CCD assembly, we will see on the front the image sensor. I got some pretty cool shots of it, but I can't really zoom in far enough to see the individual pixels. You can see that there are two lines of each color and it is supposed to have 4 lines, so I assume there are staggered pixels under each of the color filters. And the ADC and processing chip is likely underneath this cover, which we can't easily remove because it is soldered on. I've now hooked up my logic probes to the data lines on the connector, which goes from the main control board to the CCD board. 8 data lines, 2 clock lines, 1 chip select, a reset pin, and the rest seems to be just supply voltages. And now with the scanner idle, we can see that only the reference clock is running. Now when I start up the scanner, we should see some activity. And now it noticed that there is no reflective strip and it's in the default state again. To guess the communication protocol, I've looked at the schematic of a different scanner, the V200, which lists the D6 and D7 pin as S-clock and SDIO. Now I want to show you the process I've been using to capture the setup commands, which are sent by the main controller to the CCD interface. I already know that the pins D6 and D7 are being used as a half-duplex SPI. So I have set up a protocol with the D7 as the clock and D6 as a data pin and a separate CS pin. I'm using SPI serial triggering to capture this data, and when I start the oscilloscope, we will see a lot of data coming in. I've set it to a pretty slow time base of 20 milliseconds per division, and I will immediately stop the capturing once it is starting to sample image data, so we know what comes before that. And stop. And here we can see that there's really a lot going on, and when we zoom in here, yeah, and now it is showing us all the data which is being sent. So there are separate blocks, and the most important thing are these blocks before it actually starts sampling. This one and these ones. I saved all of them using the decode result list function, and then I can save all of this to a network drive on my PC and import it into Excel, for example, and try to decode this data. Now we can open the data we captured on the oscilloscope, and we see that this is only the last block, the last packet I've captured before it actually started sampling and afterwards, and it's 231 packets, and this is already entered into a different table where I'm currently trying to decode it. And one of the packets, for example, which I was able to cross-reference with a different datasheet. I do not have a datasheet for this exact chip. That seems to be completely secret, but I was able to find a Japanese datasheet of the S7R77021. One notable register, for example, is the 78, 79, and 7A, and these seem to be exactly the red, green, and blue gain and offset registers. These seem to be the timing patterns which are listed in this datasheet. Seems to mean what pins are active in what sequence and how to push out data out of the CCD. This is basically just constants which I have to send. All of this. And it gets interesting again in this part. This seems to be starting the timing generator and stopping it. It is a different register than in this datasheet. I'm quite sure that it is the same thing as this register, because when I set this bit, then it starts outputting a lot of data, which we see on the oscilloscope here. Yeah, when I zoom in, now you can see that 6, 0 and 8, 1. That is the last thing which is sent. And for the protocol, the different datasheet of the R77021 also has SDIO pins and shows that the most significant bit is read or write. And then it's supposed to go high Z when reading something, and then it will send the data. And that's exactly what I implemented. And I'm just using software bit banging of the pins because it is quite slow. And that allows me to use the same state machine which I use for reading the data on the Pi Pico or Raspberry Pi 5. So in the code, this just looks like I'm sending data by setting the pins of the state machine to output mode, the data pin plus 6, which is pin 6 and 7. Then I set the clock and clock out the data just by shifting the buffer I want to send. And for reading the data, it's pretty much the same. I first clock out the 8 bits of the register address and set the read bit. And then I read the next 16 bits using GPIO get and set the pins back to input mode. Now I have connected the original scanner head to a Pico 2, which has enough RAM to buffer a full line. The schematic was actually from the V200, so it might be slightly different on the V300. And I'm now trying to transfer the data via full speed USB, which is quite slow. And then it's going to be written into an image file. And when I go very slow, we should be able to see some text appear in the Windows Photo Viewer, which is actually updating when I write the file again. And this is using the gains and constants I sniffed from the original scanner. Otherwise, the colors will not look right. Okay, now we can see that we have some text. The image starts here and ends here. So it is not filling the whole data. There's a lot of empty data in front. Yeah, and we can also see that in this white text, we are going over the red, green, and blue sensors one after another because they are not in the same position. Especially here you can see blue, green, red, and then it goes white. So we need to compensate for this pixel shift while writing the image file later as well.
Many months later.
So let's take a look at the internal components I am currently planning to use. Of course, the CCD, which will be removed from the scanner assembly. The control interface board for the stepper drivers and connecting to the CCD board. I also want to use an SSD for storing image data and for post-processing because the images will be very large. And I also have to use a different cooler. This is the standard Raspberry Pi active cooler, so I can gain access to the screws for mounting the PCBs, which I will mount on top of the Raspberry Pi. And additionally, of course, we also need a screen. What I chose now is the WaveShare 8-inch DSi screen. This is a newer model. There's another model with a PCB somewhere here. But this one has a metal backplate covering everything and bonded to a very thick layer of glass. The benefit of this screen is that it is self-contained and only needs the DSi connector and power instead of having to deal with internal HDMI and USB connections. One of the features I want to add is a focus helper, which will basically just be a camera which can move behind the lens while I can now use the motor. I need a way to also interface the camera with the Qt application, but Lib Camera can only open up its own window or store videos. So the solution I came up with is to use Lib Camera vid to output an MJPEG stream. And an MJPEG stream can very easily just be shown in a Q label because a Q label can be a JPEG icon. And you can see that it is actually really very responsive. Now this is one of the first times I tried to assemble all of it with the CNC cut components instead of just 3D printed parts. But not everything fit together as expected, so it did take a few attempts until I worked out a order in which I could actually assemble all of it, and I did not bother to record all of them. This is one of many different sensor mounts I have printed for this until I finally got the distance between the two sensors in the same focal plane, so I can actually use this preview camera to focus properly. The distance between the sensors and the lens flange is always flat and stiff, with the metal front and M4 standoffs between the two metal plates. After many attempts and different printed case components, it was actually possible to assemble all the parts without blocking too many screws, and with everything mounted to this baseplate, it is possible to remove the whole assembly from the case without taking everything apart again. Here I am using a special cable management technique many of you will be familiar with from building PCs in small cases. It's called squishing the cables really hard between two panels and hope it never needs to be opened again. On top of the camera I have added 3 buttons, which are connected to an I2C port expander on my interface board. The connections are a little bit temporary at the moment, but it should be fine for testing. And I'm going to use these buttons to trigger the shutter, the preview, and maybe a third one. Because of the sensor size, it is not possible to use normal full-frame lenses. Initially, I looked into projector lenses, but they are usually difficult to adapt and use without aperture controls and don't work that well anyways. Ideally, a medium format lens is used. I have selected the Pentax 6x7 system for this camera because these lenses have a massive projected image, even larger than most other medium format cameras, and fully manual focus and aperture controls, and only require a very simple mount. While the system is not that common in Europe, the lenses were manufactured surprisingly long from 1969 to 2009 and are still kind of affordable even when bought from Japan, at least when compared to other medium format systems. They do require an infrared cut filter in the front because the sensor doesn't have a filter on its own, and you can pretty easily mount them to the camera like this. Just needs a passive printed mount, and then you have still full control with the manual aperture mode. One of the last major challenges to make this into a usable camera was how to actually get a usable image out of the sensor without having to process huge raw files on a powerful computer later. Obviously, the Raspberry Pi cannot store a full image at the highest resolutions in RAM, so all post-processing must be done on a short buffer instead of the whole image, and the file format must support line-by-line encoding. PNG supports practically infinite image sizes, supports gamma and color metadata, 16-bit values, and can be written and decoded line by line. The main required image processing is correcting for the sensor geometry and scan step distances. Each color has 4 staggered lines of pixels, and depending on the resolution preset, different line combinations and sprites are used. That means each line sees a certain spot on the image from different positions several lines later, so without correction the image has color offsets, or in the higher resolutions, jagged offsets within the color channels as well. To correct this, a cyclic buffer is used storing the last 16 to 100 lines depending on the resolution, and experimentally determined offsets are applied to this buffer, returning the last valid line each time. That is much more manageable than storing the whole image on a Raspberry Pi, and outputs a directly usable image. Due to the complex additional offsets, resolution limits of the old lenses, and the sublines having slightly different sensitivity, the images look best when using only the main lines at 10,000 pixels per line, and that also keeps the scan time kind of reasonable. While I would love to take this camera outside and show you some architecture and landscape shots, this camera needs a lot of light for a good dynamic range, and it is already quite late in the year because this project has been going on for several months. We will do the demo section inside, and I'm taking out this super old project you might remember from many years ago, and we are going to use this for illumination. Let's take a short look at the user interface and then take an image with this camera. I am still working on the user interface, but I would say it is pretty usable right now, and all the core functionality is already implemented. One mode, we have here different radio buttons for the modes. One mode is the debug screen, and in the debug screen I can move the motor and force homing and see where it currently is, just for checking the linear stage movement. Then we have a gallery mode, which shows all the pictures I have taken so far, how much space is still available on the internal SSD, and it allows me to also delete photos to free up space, or if an image wasn't good. That of course helps in the field when I do not have direct network access to the SSD and want to see all my pictures. Then the first photography mode is the preview mode, which can also be accessed by pressing this button. And in the preview mode, the small 2D sensor will move in the center of the lens, and I can now easily focus the image. And this gives me a rough idea where the image will be centered and what will be in focus. So the scene I want to focus on is this old stack of instruments. And you can see at the moment it is focused on this connector where I have put a little PCB with the OpenFF board logo. Now let's finally take a picture with this camera. We are focused on our target. In the preview mode, we can also move the sensor in the preview mode and see different sections of the image. And for example, I could now try and focus on this text instead, which is kind of in the center of the instrument. And then we go into the line scan mode. And in line scan mode, now I have to turn on the light. We have different gain settings for the CCD sensor. We have a gamma adjustment as metadata in the PNG file. And we can also change the resolution. In this case, I will take a picture in 10,000 pixels height. And then we have this width adjuster to change the scan width, and therefore the width of the image. Now the first thing to do is take a preview and check the scene. And this is doing a scan in the lowest resolution. And we can see that we have mostly gotten our stack of instruments. I will turn the camera a little bit to the left. And when I redo the preview scan, it will also update the image. Now I could reduce the width a bit and zoom in to see if it is focused properly. And I can also redo a preview scan using this button. And if you redo the preview scan without changing the resolution, then it will also remember the zoom stage. So I think we are finally ready to take a full image. In this corner, we can also set a delay. And after I press the button, it will wait for 2 seconds and then start the scan to reduce wobbling of this camera, because wobbling can really mess up an image. This will now take significantly longer than the preview scan, because we are now scanning with 10,000 pixels. And now the image has been taken and it is now processing it into a PNG file. In preview mode, it will directly save it as an uncompressed PNG. In the actual photo mode, it will first store it in a uncompressed raw buffer, so it doesn't interfere with the scan and the processing is minimal. And then it will re-encode it to PNG after the image has been taken. And then it will generate a smaller preview file to show in the gallery. So this is the image we have taken, and I will show it to you on the PC. So in order to copy an image from the camera, we can use Samba. There's a Samba server running, and we can connect an Ethernet cable to the Raspberry Pi and open it share. And the share is, for example, the SSD share. We can go into the images, and our newest image is this. Then I will copy it to a local drive to make it easier to edit. And for very large images, I can highly recommend using the old Windows Photo Viewer, because it is much better for viewing massive images, and it can also rotate the image fairly quickly. And yeah, as you can see, this is the image I have taken. And we can see that we are focused on the text, and there are some slight artifacts here. This is due to the sensor still sometimes exposing for a little bit too long. This is going to be fixed at some point. Yeah, we can see it is providing a sharp image. We could go significantly higher with the resolution. This is 1/4 the resolution only. And with higher resolutions, of course, the scan will take significantly longer. It has a resolution of roughly 6,000 by 10,000 and is 300 megabytes in size. Now for comparison, I also have taken an image with the 200mm lens compared to the 75mm. On the left, we have the 75mm image we have just taken. We see some slight chromatic aberration, while on the 200mm lens, here we see significantly less chromatic aberration. Obviously, it is also zoomed in a little bit more and therefore sharper. And the last mode I want to demonstrate is the line cam mode. In line cam mode, the sensor stays in the center of the lens and takes an exposure like a normal image, but without moving the sensor. I focused on this board and I will try to move my hand slowly in the same focal plane. And we can see that it has now taken an image of my hand, and the background is just one line over and over. So this mode is usually used for sporting events, finish cameras, or for photographing moving objects like cars, trains. With this camera, it would be quite difficult to take a photo of a train because it is probably too fast and the exposure time is pretty slow. You've seen how slowly I've moved my hand. But it can be used to generate very interesting effects, especially with different backgrounds and objects. I also wanted to build a panorama mode, which like turns the whole camera with a separate motor. I've seen a different project which built a camera just to take panorama pictures with a same kind of sensor, and this camera is probably too heavy to really implement this well. This was one of my most challenging and interesting projects due to the uncertainty of decoding the unknown communication protocol and overall complex integration of many different parts and processes. While it was significantly cheaper than an actual medium format camera, it still required many parts and tools and even more of my time while working on it heavily for several months. Overall, I am quite satisfied with the result. It is fun to use with good image quality, and I might continue working on it in the future and post more images taken with this camera. This video is not sponsored, so if you want to support this and other projects or learn more about it, check out the links in the description, my Patreon page and Discord community.